Alright, so in this video I want to give you a review of trigonometry. I want to talk about the coordinate definition of trig functions, the Pythagorean identity, negative angle identities, complementary and supplementary angle identities, special angles that don't require calculators, and that's essentially all that we need to focus on right now regarding trigonometry. Alright. So trigonometry is focused on certain properties of angles that were discovered many centuries ago. If you take a angle, all right, there is a picture of an angle, and let's make a triangle out of it. Actually, you could make several different triangles, several different right triangles out of the same exact angle, couldn't you? So here I have three overlapping right triangles, and they all have that same angle on the left side there. So let's call this triangle 1, triangle 2, and triangle 3. And let me label the vertical and horizontal sides of these right triangles. Okay, where F isn't just that little piece there, but the entire triangle, this entire length is F, and the entire length of the bottom of triangle 2 is D. I hope that's clear. Okay, and let's call this angle, traditionally we denote angles by Greek letters. Theta looks like a 0 with a line through it. All right, now if for all of these overlapping triangles, if you were to measure, you can actually do this on a piece of paper. Draw this out as best you can. Find A over B with a ruler. Find C over D and E over F. You will see that all of those are approximately the same. The better you measure it, the closer they'll be. Okay? If you measured, let's say, the hypotenuses of these right triangles, you would notice other ratios are the same. A over X, C over Y, E over Z. All right? And likewise, B over X, D over Y, and F over Z. All right? So in a sense, it really doesn't matter which right triangle you use for an angle. The only thing that matters is they all have the same angle. All right. Now, if you were to change the size of the angle, then these ratios would then change. Okay. Now, these ratios are given specific names. All right. Traditionally, so let's start with let me put a purple rectangle around it. So these guys are referred to as the cosine ratio of the angle. So I'll put a little theta like it's a function, which it is. And then this next box is called the sine ratio. So you can think of the sine function, gives you the ratio for that angle. And then the last one is it's called the tangent ratio of that angle, and you just draw a right triangle, measure those ratios, and then you can get those values. Now, people used to print books and tables that had these for lots, 1 degree, 2 degree, 3 degree, different sized angles. Nowadays, of course, you can just punch into your calculator and get the ratio. Okay, and so a lot, if not all, of the trigonometry that you need to know is based on what I have on the screen right now. Okay, that's a lot of it. Okay, everything else, if it's not implied by this, it's pretty darn close to what I have here, or very related to it. Okay, now it turns out somebody needed to define these ratios for like negative angles, obtuse angles, and so we're going to extend these angles. Now the definitions I have here will work as long as the angle is acute. In other words, it's less than 90 degrees. But if it's negative or obtuse, then we've got another definition that it's equivalent for acute angles, but it extends the definition for other cases. So let me talk about that now. So let's create XY coordinate axes, and let's put a unit circle. That means a circle with a radius of 1, and let's center it at the origin. Okay, now let's go ahead and draw our angle again. Angles, whatever angle we have. So if we, and because it's a circle, we know that all radii have a length 1. So if I have a angle theta, okay, and I've got, let's say that this point on the circle, let's give it the coordinates x comma y, which of course that's we know that from regular coordinates geometry. So that angle, the bottom side of the right triangle is going to have a length x. This is going to have a length y. The hypotenuse is going to have a length 1. For that situation, the sine is going to be y. Well, it's going to be just y. Let's y over 1. Later on, I'll change 1 to r. Cosine is going to be x over 1. Tangent is going to be y over x. All right, and what they did to generalize this is they said, you know what, if it's not in that first quadrant, so even if you have an angle way out here, okay, that's the obtuse one I was talking about, and let's give that a different name instead of theta. Let's say that this was angle alpha, and let's say that the coordinates of alpha are a comma b. Okay, so for that, the length of the bottom, because a is negative, the length is minus a, or you could say the absolute value of a. That would probably be cleaner. And then the height is b. Okay, and for that, just like the other one, we're going to say that the sine of alpha is, and then the hypotenuse is 1, so b over 1 cosine of alpha is, now we don't use the absolute value of a, we use a over 1. So it's always the x coordinate. Okay, when I drew there, I was drawing the length. The length is the absolute value, but the cosine doesn't matter if the cosine is negative, and it can be. And then the tangent is b over a, not absolute value of a. Excuse me, the tangent of alpha is b over a. Hopefully this is review for you. All right, and now this definition is much more powerful. You can see certain patterns now. For example, you know that for any right triangle, the Pythagorean theorem holds. Okay, so that tells you that, for example, the first right triangle that I drew, x squared plus y squared has to equal 1. Okay, that's because the hypotenuse has a length 1. All right, now using the definitions that I just gave you, can you see that that also implies that cosine squared theta, cosine squared theta plus sine squared theta is equal to 1. Okay, and what about if instead of the angle, what if I had a negative angle? So I was down here like this, minus theta. All right, well, the x coordinate would still be the same, but the y coordinate would change sign, something like that. Okay, and if I still did the same ratios, can you see that the sign would remain? Well, no, the sign would change because the y value changed. The cosine would be the same because the x is still positive. The tangent would change because the sign of the y changed. So all that is to say that the sine of negative of an angle is this, it doesn't change. It's the sine of the without the sign change. But the cosine, excuse me, I know I did that wrong. Let me backtrack here. So the cosine remains the same. So cosine of negative theta is cosine of theta. The sine of negative theta, that one changes sign. That's minus sine of theta. And then tangent of minus theta is minus tangent of theta. Okay? Let me go to a new page now. So we know that the angles of a triangle have to add up to 180. So if I have let's say I have an angle here, theta, this one has to be 90 degrees minus theta. If I call this x, let's not use x because we already used that, had special meaning in the last slide. Let's use A, B, and C. Okay, so the sine of theta is going to be, now if you're talking about a acute angle like I am here, then you can forget about the circle and the x and y and all that, and just know that you just use the ratios. So for the sine, it was you might recall when I first started talking about this, it was the opposite to the adjacent, or the angle next to the, the side length next to the angle. That's not the hypotenuse. And then the cosine would be there was the one that was next to it, but that wasn't the hypotenuse. And whoops, let me fix my sign. It's b divided by the hypotenuse. All right. Now, just for the heck of it, let me go ahead and take the sine of 90 minus theta. So that's the other angle up there. So the opposite divided by the hypotenuse. And let's do the same thing for the cosine. The opposite to 90 minus theta is A. Cosine is adjacent over hypotenuse. So this would be B over C. All right. And notice that we have some things that are equal. So these two are equal, and these two are equal. All right. So this is how you can accept another identity, which is that the sine, I'll put it in the bottom left. So the sine of an angle is equal to the cosine of 90 degrees minus the same angle. Likewise, the cosine of an angle is equal to sine of 90 degrees minus an angle. Very good. And then for most ratios, you will have to plug these into your calculator because nobody could memorize this stuff. It turns out there's a few angles where you can memorize it, you can derive it yourself. Let me show you how that works. So let's start with an equilateral triangle. That means all sides are the same. Let's chop it in half and make two right triangles that are congruent. So because I started out with an equilateral triangle, and let's make the sides of length 1. Okay, so all the angles have to be the same. That means they can only be 60 degrees. Okay, now that I chopped the top angle in half, we know that therefore each half has to be 30 degrees. And we know that I chopped the bottom leg in half, so that means each of these pieces is a half. Okay, well, take a look at this. Let me make a copy of the left half. Okay, whenever you have what's called a 30, 60, 90 right triangle, these will always have these ratios. The hypotenuse and then the bottom side will be half the length of the hypotenuse. And by Pythagorean theorem, you can derive that the vertical has to be length square root of 3 over 2. All right. Now here is another. That's one special triangle, 30, 60, 90. Let me now show you the only other one. So if you had a isosceles right triangle, so that means two sides are the same, then the only way, like let's say this is 1 and this is whatever. So if that is 1 and the other two are exactly the same, the only way that Pythagorean theorem can hold is if they have that length. And the only way that both of these angles can be the same is if they're both 45 degrees. Okay, so all of that is to now say that you can impress your friends by writing down a bunch of sines, cosines, and tangents without using a calculator. So the sine of 30, looking at the green triangle, opposite over hypotenuse, so that's 1/2. The cosine of 30, adjacent over hypotenuse. The tangent of 30, opposite over adjacent, so 1/√3. And you could do the same thing with the 60 degrees. And then, so let me go ahead and do that. The sine of 60 degrees, opposite over adjacent, √3/2. Cosine of 60 degrees, adjacent over hypotenuse, 1/2. Tangent of 60 degrees, opposite over adjacent, √3. Let me now do 45. Cosine of 45 degrees, adjacent over hypotenuse, 1/√2, or if you like, √2/2, same thing. The sine of 45, you will see, is, well, it's the same thing, 1/√2 or √2/2. And then the tangent of 45 degrees, opposite over adjacent, that can only be 1. All right, and that concludes the trig review for this video.